Here's a deceptively simple question that nearly every Python data science interview includes. How are lists, tuples, sets, and dictionaries different? Now, most candidates start listing definitions. But interviewers don't want definitions. They want to see if you know which one to use, when, and why. So here's the quick and confident way to answer. A list is your go-to for storing data that changes, it's ordered, supports duplicates, and is completely flexible. For example, think of tracking daily sales. New numbers keep coming in, and lists let you grow dynamically. A tuple looks similar but is fixed. Once created, it never changes. That's perfect for constants like geographic coordinates. Latitude and longitude don't need to be edited mid-analysis. A set holds only unique items, no duplicates, no order. It's ideal when you need to clean data or test membership quickly, like removing repeated customer IDs. And a dictionary stores key value pairs. Think of it like a quick access mini database. If you want to map user IDs to purchase totals, a dictionary gives you instant retrieval speed. So when you get this question, focus on mutability, order, and performance. That's exactly what the interviewer is testing, not memorization, but how you think about structure. Let's go a layer deeper, because the real power of these structures comes from knowing how to use them in real data science pipelines. Here's how they play out in practice. Lists in action. Lists are mutable, they grow as new data arrives. Imagine you're building a feature vector. Each new transaction adds another element. Lists are perfect when your data changes frequently during training or feature engineering. Tuples as constants. Tuples are immutable. Once created, they stay locked. You can use them to store fixed information like latitude-longitude pairs or system configurations that shouldn't change accidentally during model runs. This makes your code safer and easier to debug. Sets for speed. Sets store unique elements only. They're brilliant when cleaning datasets, for example, removing duplicate customer emails or finding all unique product SKUs. And they're lightning fast for membership testing. Checking if a user already exists in your dataset takes milliseconds. Dictionaries for mapping. Dictionaries are your key value engines. They're used everywhere in machine learning. For example, caching model predictions so that identical inputs can be retrieved instantly instead of rerunning computations. They also form the backbone of JSON-like data structures you pass to APIs. Now, here's how you can confidently frame this in an interview. In one of my analytics projects, I used sets to instantly identify overlapping customers across multiple marketing segments. It cut comparison time from minutes to milliseconds. For configuration management, I switched lists to tuples to prevent accidental data changes during model runs. And for caching, I used dictionaries to store model predictions that improved overall pipeline speed by almost 30%. Knowing when to use each type made my code both faster and safer. That kind of answer doesn't sound memorized, it shows real engineering judgment. It tells the interviewer, you don't just write Python, you understand how data structures drive performance and reliability. Here's a question that sounds simple but often trips up even experienced Python developers. What's the difference between a shallow copy and a deep copy? Now, both of these make copies of objects in Python, but they behave very differently, especially when your data is nested. Let's keep it simple. A shallow copy makes a new outer container, like copying a folder. But all the files inside still point back to the same originals, so if you change something inside, both folders reflect that change. A deep copy, on the other hand, doesn't just copy the folder, it duplicates everything inside it too. Each file, each subfolder, brand new and fully independent. That's the key difference. Shallow copy 12 shares inner references. Deep copy 12 creates completely separate objects. Interviewers use this question to test if you understand how data is linked in memory, because that can make or break your pipeline's reliability. Let's break this down with an example. Imagine you have a list of lists, like a dataset with two small tables. When you make a shallow copy, Python creates a new outer list. But the inner lists, the tables themselves, still point to the same memory. So if you update one table in the copied version, the same change appears in the original, even though you didn't touch it. Well, now, when you use a deep copy, Python duplicates everything, the outer list and all the inner lists inside it. Now the two are completely separate. Changes in one don't affect the other. That's why deep copies are essential when working with nested data, like dictionaries inside lists or configurations inside models. Let's see how this matters in real life. In one of my A/B testing projects, we had a configuration dictionary for each experiment variant, A and B. Each config had nested parameters for model settings and data filters. At first, we made a shallow copy of variant A's config to create variant B. But when we tweaked one nested value for variant B, it also changed inside variant A, because both shared the same inner reference. That bug silently broke our test results. Both experiments were running the same setup. After that, we switched to DSeep, which created truly independent versions of each config. That small change prevented the overlap, gave us clean results, and saved hours of debugging time. Here's how I'd say it in an interview. In one of my experiments, I used DC to create separate configurations for two A/B test variants. Before that, using a shallow copy caused the nested parameter dictionaries to share references. So updating one variant changed the other. After switching to deep copies, each configuration became independent, and our test results were finally reliable. That answer shows you understand not just what shallow and deep copies are, but also why they matter, especially when you're working with nested data structures in machine learning or analytics. Here's a deceptively simple interview question that tests your Python efficiency and scalability mindset. What's the difference between list comprehensions and generator expressions? Let's make it easy to visualize. When you use a list comprehension, Python builds the entire list in memory right away. It's fast for access, but it consumes memory because the whole dataset is stored at once. Now, a generator expression looks almost the same, but it's lazy. Instead of building everything up front, it produces one item at a time only when you ask for it. So the difference is simple but powerful. Lists trade memory for speed. Generators trade a bit of speed for massive memory savings. Think of it like downloading an entire movie before watching, versus streaming it as you go. Both work, but one saves a lot more data. Let's break this down in code, in plain English. When you use a list comprehension, Python loads everything into RAM. Imagine you're extracting features from a data frame. You loop through every row, collect results, and hold the full list in memory. That's perfect for small datasets, because you can reuse it, debug it, or access elements randomly. But when your dataset explodes, say 50 gigabytes of log files, storing everything at once will crash your system. That's where generator expressions shine. They don't store all results, they yield one row at a time. It's like an assembly line. As soon as you're done with one record, the next one arrives. That means your memory usage stays almost flat, even with massive data. Now, here's how I'd explain this in an interview. When I was processing 50 gigabytes of log data, I initially used list comprehensions to parse each record. It worked, but my script kept crashing because it tried to load everything into RAM at once. I switched to generator expressions instead. That small change dropped memory usage from around 64 GB to just 2 GB, and the pipeline ran smoothly. Now I use generators whenever I'm dealing with large or streaming data, and list comprehensions when I'm working with small datasets or need random access for debugging. That's a complete answer. It shows that you understand not just Python syntax, but also how to think like a data engineer. So remember this rule of thumb. Use list comprehensions for smaller datasets you'll access repeatedly. Use generators when scalability and memory efficiency matter most, like in ETL pipelines or log processing. Here's a classic question that comes up often in Python, data science, or machine learning interviews. How does Python handle namespaces, and what exactly is the LEGB rule? Now, this question isn't about memorizing what the letters stand for. It's about showing that you understand how Python knows which variable you meant. That understanding becomes critical when debugging, working with closures, or writing modular ML code. Here's the intuition. Every time Python sees a variable name, it looks for it step by step, in a specific order. That order is called LEGB, which stands for local, meaning variables inside the current function, and closing, meaning variables from an outer or nested function, global, which are variables defined at the module or file level, and built-in, which refers to Python's predefined names, like len, print, or range. Think of it like a search ladder. Python starts from the narrowest box, your local function, then moves outward through enclosing and global. and finally looks into the built-in scope if it still hasn't found what it's looking for. The moment it finds the name, it stops searching. And that's the key idea behind Python's scope resolution, the LEGB rule. Now, let's bring this to life with a simple example. Imagine you define a variable at the top of your file. That's global. Inside a function, you define another variable with the same name. That's local. And inside a nested function, you define it again. That's enclosing. When Python needs that variable, it starts by checking the local function first. If it doesn't find it there, it moves to the enclosing function, then to the global scope, and finally to the built-in names like len or print. That's Python's LEG search process in action, step by step, from the smallest scope to the largest, and the moment it finds the variable, it stops searching right there. Now, here's why this matters in real-world data or ML projects. If you're building a model training pipeline, you might define metrics like accuracy or loss at a global level, then try to update them inside a local training function. If you forget to declare them as global, Python treats them as new local variables, and suddenly your metrics stop updating, or you get an unbound local error. Here's how you could turn that situation into a strong interview answer. While debugging a metrics aggregator in one of my ETL jobs, I realized my counter variable wasn't updating. It turned out I was modifying it inside a function, and Python was treating it as a new local variable instead of the global one. Once I understood the LEGB rule, I fixed it using the global keyword and later used enclosing scopes to design closure-based configurations for data transformation functions. That approach helped each function maintain its own state without interfering with others. That's the kind of answer that interviewers love, because it shows you understand how Python works under the hood and how that knowledge makes your data pipelines and ML workflows cleaner, safer, and more modular. So the next time something weird happens with your variables, remember this. Python always looks in this order: local and then enclosing and global and last built-in, and it stops as soon as it finds a match. This is one of those interview questions that sounds easy but separates beginners from people who've really used Python. What are Python's key data types, and how do you use them in data science? Now, the interviewer doesn't just want you to list data types. They want to see you understand when to use each one. Here's a clear, structured way to answer. Python gives you 5 core data types that power almost every data science task. Numeric types, integers and floats, are for calculations. If you're summing up sales revenue or finding the average rating of a product, you're using numerics. Sequences, lists, tuples, and strings hold ordered data. Imagine a list of daily temperatures, or a string storing customer feedback. That's a sequence in action. Mappings, dictionaries, store key-value pairs. Think of them like labeled storage boxes, user IDs mapped to purchase totals, or product names mapped to prices. Sets hold only unique items. If you want to find all distinct countries your customers are from, a set gives you that instantly. And booleans, your logic controllers. They answer yes or no questions, like whether a transaction is fraudulent or not. Each type serves a specific purpose and affects speed and memory. Choosing the right one can make your analysis far more efficient, and that's what interviewers are really testing. Let's unpack how these data types show up in real data science work, because that's where most interview answers fall short. Every Python data type is designed for a particular kind of task. Integers and floats handle numerical computations. If you're calculating revenue growth, total orders, or model accuracy, that's numerics at work. Strings and lists help process text and sequences. For example, a list might store each step in a customer's journey on your website: homepage, product page, cart, checkout. A string could store their written feedback: loved the fast delivery. Dictionaries give you super fast lookups. Picture a phone book: names as keys, phone numbers as values. In data science, we use this idea to map user ID to their data, or product codes to their details. Sets are great for cleaning and comparison. Say you have 1 million customer emails and want to know how many are truly unique. Converting them to a set gives the answer instantly. And booleans help drive control logic. For instance, you might filter only true values where churn probability is above 0.7. That's booleans guiding decisions. Now, here's how it all fits into a real project. In an e-commerce analytics pipeline, we used floats to calculate conversion rates and revenue, dictionaries for user profiles and product catalogs, lists for time series clickstream data, sets to find unique visitors, and booleans to flag returning customers. That combination reduced processing time by nearly 40% and made queries 3 times faster in production. Here's how you can phrase it in your interview. In my Turn project, I used dictionaries to map user IDs to features, lists to track user actions in order, and sets to remove duplicate transactions. Choosing the right type reduced runtime by 40%. That kind of example proves you understand not just Python, but how to think in data structures, which is what truly sets apart great data scientists in interviews. This is one of those interview questions that looks simple, but actually tests whether you understand how to write clean, reusable, and production-grade Python code. The question is, what are Python decorators, and can you give an example from a data pipeline? Here's the simplest way to think about it. A decorator is like a smart wrapper that adds extra features to your function, without you changing its actual code. So, imagine you have a function that trains a machine learning model. Now you want to measure how long it takes, but you don't want to clutter that function with timing code. A decorator lets you wrap that function and automatically add the timing feature, cleanly and consistently. It's like putting a gift inside a box. The contents stay the same, but the box adds presentation and structure. In Python, we use the @ to apply decorators. It's just a cleaner way to attach extra functionality like logging, validation, retries, or caching. In interviews, they're looking for 2 things. Do you understand how decorators help keep your logic clean and modular? And can you show where you'd actually use one in a real data workflow? Let's look at how decorators actually work. In this example, we define a timer decorator. It measures how long any function takes to run. Inside it, we first record the start time, then call the original function, and finally calculate how long it took. Instead of changing the function itself, we simply wrap it. Then, by writing a timer above any function, like our model training function, Python automatically applies the decorator. That means every time the function runs, it prints its duration, without us writing a single extra line inside the original code. This is the beauty of decorators. They let you extend functionality transparently, keeping your core logic simple and focused. Now, let's connect this to a real project scenario. In one of my ML pipelines, I built a cache result decorator that stored expensive feature computation results in Redis. Normally, these transformations took around 45 minutes on repeated runs. But by caching the results using the decorator, I reduced it to just 8 minutes, without changing a single transformation function. The decorator handled all the caching logic, keeping the business code clean and reusable. That's a perfect way to answer in an interview. It's technical but practical. You can also mention other real-world decorators, @retry for handling flaky API calls, @validate schema for input validation, @log performance for monitoring, and authentication for endpoint security. So, if you ever want to sound like someone who writes production-level Python, decorators are your best friend. They show that you understand modularity, reusability, and clean architecture. This is one of those Python questions that sounds technical but really checks how you think about data and memory. What's the difference between mutable and immutable objects? Here's the simplest way to understand it. A mutable object can be changed in place. Think of it like a notebook. You can open it, erase something, and write something new without buying a new notebook. Lists, dictionaries, and sets work this way. You can keep updating them as your data changes. An immutable object is like a printed receipt. Once it's printed, you can't change it. If you want to update it, you print a new copy. Strings, tuples, and numbers in Python behave this way. So in short, mutable is editable, immutable is fixed after creation. And this difference really matters, because it changes how Python handles memory and variables. Sometimes, a single small change can update multiple references without you realizing it. Let's see why this matters in real projects. Imagine you and your teammate are both writing on the same whiteboard. That's a mutable object. If one of you changes something, the other immediately sees it. That's convenient, but risky if someone accidentally erases something important. Now imagine each of you has your own printed copy. That's immutability. You can make your own edits safely without changing anyone else's copy. This difference affects debugging, performance, and even model reliability in production. Here's a simple example. Suppose you create a list in a function that keeps track of metrics like accuracy. If you forget to make a new list each time, Python reuses the same one from before, so you call the function twice, and suddenly your old data appears again. That happens because lists are mutable. They change in place. To fix that, you can make a copy or use an immutable type like a tuple when you want to keep data frozen. Now, let's talk about a real project example. In one of my model tracking systems, we used immutable tuples as dictionary keys. Each key stored the model name, version, and parameters. Because tuples never change, our cache stayed stable even with 50 users accessing it at once. If we had used a mutable list there, it could have caused inconsistent lookups and corrupted data. Now, here's how you'd explain this in an interview, clearly and completely. In one of my projects, I built a small function that tracked metrics like accuracy and precision after each model run. I used a list to store those results. But after running the code several times, I noticed something strange. The list kept growing, even when I hadn't added any new data. That's when I discovered the issue. Lists in Python are mutable, meaning they can change in place. Every time the function ran, Python reused the same list from before instead of creating a new one. To fix it, I made sure to create a new list inside the function each time, or use .copy when I needed a fresh version. Later, I also started using tuples, which are immutable whenever I wanted to make sure data stayed fixed, especially for configurations and model settings. That small change made my code much safer and easier to debug because I knew exactly where changes were happening and where they weren't. That experience taught me to always think about how Python handles memory behind the scenes. Understanding mutability helped me avoid subtle bugs and write cleaner, more predictable code, which is crucial when you're working on data pipelines. That's a complete, real-world answer. It shows that you understand the concept, can spot a bug, and know how to apply immutability strategically to build more reliable, production-ready systems. And that's exactly what interviewers are looking for. Here's a classic Python interview question that sounds simple, but it separates people who really understand how Python works under the hood. The question is, what's the difference between the word is and the double equals operator? At first, they both seem to check whether two things are the same, right? But in reality, they're checking two very different kinds of sameness. When you use double equals, Python checks if the contents of two objects are equal. For example, if two lists or arrays have the same values inside them, it's basically asking, do these two look the same? But when you use the is keyword, Python checks if both variables actually point to the exact same location in memory. So it's not about what's inside, it's about whether they are literally the same object. It's like asking, are you both referring to the same thing? Here's the easy way to remember it. Double equals means same value, is means same identity or same memory address. Interviewers love this question because it reveals whether you understand Python's object model and how memory references really work behind the scenes. Let's bring this to life with a simple example. Say you have two lists, both with the numbers 1, 2, and 3. If you compare them using double equals, Python says they're equal because their contents match. But if you check them using the word is, Python says they're not the same because even though they look identical, they live in two different places in memory. Now, if you assign one list directly to another variable, for example, by saying C equals A, and both variables point to the same object, at that point, both double equals and is will return true because they're literally two names for the same object in memory. Now, here's why this actually matters in real data science or machine learning code. Imagine you're checking whether a variable is none. Many developers accidentally write double equals none, but the correct and faster way is to use is none prime. Because is checks identity and none is a single object in memory. That one habit helps you avoid subtle bugs in data cleaning or model initialization steps. There's another interesting twist, Python's interning. For small integers or very short strings, Python sometimes reuses the same memory location internally to save space. So when you check identity on small numbers like 256, you might get true, But for larger numbers, like 257, you won't, because they live separately in memory. Now here's how you can wrap this up confidently in an interview. In Python, the double equals operator checks if two objects have the same value, while the is keyword checks if they're actually the same object in memory. I use is for things like none, true, or false, and double equals for comparing values or arrays. Once, I debugged a caching issue where two different data frames were returning equal values but were stored in separate memory locations. Using identity checks helped me track down the duplicate references and fix the bug. That kind of answer shows not only that you know the theory, but that you can apply it in real-world debugging and data engineering. So remember, double equals checks what's inside, is checks where it lives. That's the level of clarity interviewers love to hear. Here's a question that looks technical but actually tests how deeply you understand what's happening under Python's hood. How is memory managed in Python? Now, the good news is Python manages most of it for you automatically. But under the surface, it's doing three really smart things to keep your code efficient. First, it uses reference counting, which means Python keeps track of how many variables point to a particular object in memory. When that count drops to 0, meaning nothing's using it anymore, Python automatically frees it. Second, it has garbage collection, which steps in for more complex cases, like when two objects reference each other and can't be freed by counting alone. And third, Python uses memory pools, more and more VO, a built-in system that recycles small chunks of memory efficiently, so objects are created and destroyed faster. In an interview, what they're really testing here isn't memorization, it's whether you understand object life cycles, memory leaks, and how to keep large-scale pipelines running efficiently without crashing. Let's see how this works in practice. In Python, every object keeps a small internal counter. It's like a popularity score. Each time you assign that object to a new variable, the score goes up. When one of those variables is deleted or goes out of scope, the score drops. Once it hits 0, Python knows the object isn't needed anymore, so it automatically clears that memory. But here's the tricky part. Sometimes two objects can keep referencing each other, forming what's called a circular reference. When that happens, the reference count never reaches 0, even though nothing else in your code is using those objects. For example, imagine two simple nodes, A and B, that each hold a reference to the other. Even after your function ends, they're still keeping each other alive. That's where Python's garbage collector comes in. It periodically checks for these loops and cleans them up safely. Now, let's make it real. Here's how I'd explain this in an interview with a story. In one of my recommendation pipeline projects, we were processing over 10 million records daily. I noticed the system memory kept growing after each batch run, a classic sign of a memory leak. Using sys.getRefCount, I found out that cached data frames were holding circular references through custom wrapper classes. Once I understood how Python's reference counting and garbage collector worked, I added proper cleanup inside our destructor methods and switched to weak references for observer patterns. That small fix reduced our memory footprint from 16 gigabytes to just 4, and the system ran 3 times faster without restarts. That's a confident answer. It shows you don't just know Python's memory model, you can use it strategically to debug, optimize, and scale data pipelines in production. Here's a question that almost every data scientist or machine learning engineer faces in an interview. How do you handle large datasets efficiently in Python? Now, this question isn't just about knowing the tools. It's about showing how you think when data doesn't fit into memory. Let's break it down. The first strategy is chunking and streaming. Instead of loading an entire dataset at once, you load it in smaller batches. For example, a few thousand rows at a time. You can do this using pandas by reading the data in chunks, or by using generators that stream one piece of data at a time. This helps avoid memory errors when working with massive CSVs or log files. Next, we have data type optimization. Most people forget this, but changing a column's data type can cut memory usage in half or more. For example, converting a 64-bit integer to a 32-bit integer, or changing long string columns into categorical types, can make your data processing 2 to 3 times faster. Then, there's parallel processing, using libraries like Dask, multiprocessing, or joblib to split your workload across multiple CPU cores. This is great when you're cleaning or transforming independent data chunks. And finally, out-of-core computing. That's when you use disk-based tools like databases, Parquet files, or memory-mapped arrays, so Python processes data directly from storage, rather than keeping everything in RAM. In short, the interview is testing whether you can think at scale, understand memory constraints, and know when to move from single machine processing to distributed solutions. Let's see how this works in practice. Imagine you're reading a massive CSV file, maybe hundreds of millions of rows. If you try to load it all into memory, your machine will crash. Instead, you read it in chunks. For example, 100,000 rows at a time. Inside a simple loop, you process each chunk. Maybe you're cleaning a column, adding a new feature, and then saving that process chunk to a list or writing it to disk. Once all the chunks are done, you can join them together into a single data frame, or save them to a Parquet file for downstream use. This approach lets you handle datasets far larger than your computer's memory, because you're only working with small pieces at a time. Now let's talk about data type optimization. Suppose your dataset has integer columns that don't need to store huge values. You can safely downcast them from 64-bit to 32-bit or even 16-bit integers. For floating point numbers, you can use a smaller precision type. And for text data, converting long repeated strings, like category names, into Pandas's categorical type can reduce memory by 80 to 90%. Together, these two techniques, chunking and type optimization, can turn a job that crashes your laptop into one that runs smoothly in seconds. Now here's how you could explain this in an interview, clearly and confidently. When dealing with large datasets, I usually combine chunking with data type optimization. For example, while processing a 20 GB clickstream log, I read the data in batches of 100,000 rows, applied transformations to each batch, and downcasted numeric and string columns to save memory. This reduced RAM usage from over 16 GB to just under 3 GB, and cut total processing time by more than half. I also use Dask or JobLib for parallel execution when the job can be distributed, and switch to disk-based formats like Parquet for out-of-core computations. That kind of answer shows you understand scalability, performance tuning, and production-level data handling, and that's exactly what interviewers are looking for when they ask this question.